Okay, so what we're going to do in this is we're going to walk through the first part of the paper 1 exam, which is the multiple choice part of the exam we're going to look at today. And just like with the other parts, we're going to go through each question one by one. I'm going to explain how to approach the question, the thought process behind working out the answer, and then of course tell you the correct answer as well as looking for any potential traps or pitfalls in the question. Because it's a video, the idea is of course that you can jump forward, skip back and go through each question at your own pace, and of course there's no point you looking at a question that you know you got right. Before we start, there's two things that are worth saying about a multiple choice paper. The first one is that it is not as easy as people think. Right? It's very easy to look at a multiple choice paper and think, that's going to be the easy paper. That is not true. In fact, it's almost the opposite. With an extended answer paper, your whole point is you're trying to work out what the answer is. For a multiple choice paper, you're trying to work out which answer is the right one. So that means it's very easy to fall into traps, right? And that is what the answers are meant to be. The 4 or 5 answers that you have the choice from, they are meant to be traps, right? So all of them could look right from a certain aspect, but actually only one of them will be. And you'll see that when we're going through this paper that actually a few of these questions are almost trick questions. They're not trying to trap you on purpose, but they are giving you options which you could very easily think are right if you're not thinking about the answer or the question in the correct way. So that's the first thing to bear in mind, that actually you do need to spend a lot of time paying attention to these questions. The second thing is that in a multiple choice paper, you should never ever leave an answer blank, right? Even if you have no idea, you have a 25% chance of guessing the right answer. So there is no reason to ever leave a question blank if you don't know the answer. You should absolutely just have a go, right? Even if you're not sure. And through a process of elimination, you should be able to work out which ones probably are wrong, and therefore you can actually narrow down those chances to being even maybe a 50-50, whether you are correct or not. So bearing those two things in mind, let's have a go at these questions. So question 1 is not actually about any physics content, it's about physics equipment. So it's the way you engage with the practical. So for this question, we'll ask which instrument is used to accurately measure the diameter of a thin metal wire. The key word there being that it is thin, okay? If it's thin, we are talking smaller than millimeters, right? Because most wires are about 1 millimeter in size. So what we can start doing now is we can go through the options and work out which one is the most appropriate. So a 30 centimeter ruler, I know a 30 centimeter ruler goes down to about millimeters, but we've just said that a thin wire is probably smaller than millimeters, so that's not going to be the right answer. A measuring tape tends to go to millimeters if you're lucky. It's probably bigger, it's probably centimeters or half centimeters. So again, that's too big. A meter ruler is going to be in centimeters and millimeters as well, so that is going to be too big. So the final one, by process of elimination, I already know that that is the correct one. I can also tell because it is called a micrometer. Now you don't need to be a genius to know that micro means very small. So you know that this is for measuring small things, so you should immediately be thinking, yes, this is the correct answer. If you don't know, a micromillimeter can measure to 1,000th of a millimeter. So it's really, really tiny. So that is an excellent choice of equipment to use in that situation, right? And you can see here that I'm making it very clear which one is my correct answer. If, for example, I got it wrong, if I had said that my answer was A, and then I decided that's not the case, I should be making it very clear that that is my change, okay? I want to make it very, very obvious that I'm crossing this out. Some people do kind of like tiny little squiggles to try and show that that's wrong. No, don't take any risks. Be really, really obvious that this is what I'm saying. This is the wrong answer. Question 2. A parachutist is falling through the air at terminal velocity. So we know it's at terminal velocity, which means it is a constant speed, and we know the forces are balanced. So which of these statements is correct? I'm going to do the same thing. I'm going to go through and try and work out which of these is right and which is wrong. So I'm trying to cross out the wrong ones. So every force acting on the parachutist is equal to 0 and his acceleration is equal to 0. Now that bit, the acceleration is equal to 0, that is true, but a parachutist definitely doesn't have forces of 0 because they have gravity, right? Gravity is going to be acting on them, their weight is pulling down on them, so that force is not 0, so we know that that is wrong. Next one. Every force acting on the parachutist is equal to 0, so it's the same problem, right? And it said velocity is 0, which we know isn't true because we know it's moving, so definitely not. C. The resultant force acting on the parachutist is equal to 0. Okay, so it's the total force now is equal to 0, that makes sense. And the acceleration is equal to 0. So that sounds pretty good. That might be the right answer. Last one. The resultant force acting on the parachutist is equal to 0 and the velocity is equal to 0. So the resultant force is equal to 0, that is correct. So I like that bit. But I know the velocity is not 0 because they're moving, so that's wrong. So it must be C. Notice how I'm going through every single answer. Even if I know C is the one I want to choose, I am going on to D just to check, because if they both seem right, then I have a problem. So I need to make sure I check every answer first. Question 3. The curved line on the graph shows the motion of a car. And first thing to notice, this is a speed time graph. Not distance time, it's speed time. So this line is telling me how fast the car is going. That means if this line is telling me the speed of the car, the gradient, remember gradient is y divided by x. Yeah, I know gradient is that, which means it is the change in speed divided by the change in time. So change in speed divided by time is acceleration. So this question, I already know that the gradient is the acceleration. Now, what is the acceleration of the car at time 4 seconds? They've already drawn on here for us the 4-second line here, so we know that this point is where these two lines are in contact. That means that this line, coming up here, that is the gradient I'm looking for. So what I'm going to do is my change in y, which is from here to here, divided by my change in x, from here to here. So change in y is 12 minus 3. 12 minus 3 is 9 meters per second. The change in x is 5 minus 2, so that is 3. So I'm going to do acceleration is 9 divided by 3, which is 3. Let me check. There's the correct answer. Okay, so we're happy with that. Next one. Question 4. The diagram shows a bird in flight. The bird is flying in a horizontal direction to the right. So I know the bird is flying this way. In which direction is air resistance acting on the bird? So remember, air resistance always goes in the opposite direction to the direction you're moving. So if I'm moving this way, air resistance goes in the opposite direction, so it must be going that way. That is D, okay? So I'm circling the answer here. A few people drew arrows on it. That's not telling me what the answer is. You can't draw an arrow and then trust the examiner's going to tell that it's the same as the answer you're trying to pick. You need to actually circle the answer. Question 5. The gravitational field strength on the moon is 1.6 newtons per kilogram. An astronaut has a mass of 75 kilograms. What is the weight of the astronaut on the moon? So I need to remember that the equation is weight is mass times gravity. So I'm going to do 1.6 times 75. 1.6 times 75 is 120. 120 is one of the options. Good job. So I'm going to circle that. Question 6. A measuring cylinder contains 30 centimeters cubed of a liquid. Some more of the liquid is added until the level reaches the 50 centimeter cubed mark. The reading on the balance increases by 30 grams. What is the density of the liquid? So I know that density is mass divided by volume. Now, the volume is not 50, it started at 30. So what I need to be doing is 50 minus 30, and that's going to give me the change in volume. It's the volume I've added, right? So 50 minus 30 is 20 grams. And then the volume, it told me, that is the volume. So that's centimeters cubed. Then the mass is going to be 30 grams, which was here. So to work out the density, I'm going to do 30 grams divided by 20 centimeters cubed. And if I do that on my calculator, I go 30 divided by 20, that is 1.5. 1.5 is one of my answers here, so that is going to be my correct answer. Okay, now you can see how this is actually trying to trap you, right? Because if I had got those the wrong way round, if I'd done this wrong and said it was 20 divided by 30 instead of 30 divided by 20, I've got 0.6. So you can see that that's that answer. So that's the wrong answer, but it's one of the options still, and it's easy to make that mistake. The same, you can actually get these other answers by using the numbers wrong. So you need to be very, very careful that the calculation is correct. That is what I was saying at the start about these questions aren't traps, but they are making it easy for you to make mistakes. So you need to be careful. Question 7. So a stone of mass 0.12 kilograms is fired from a catapult. The velocity of the stone changes from 0 to 5 meters per second in 0.6 seconds. What is the average resultant force acting whilst being fired? So, I have got a question about force. So I need to be thinking, what are my force equations? Okay. And the one I know, which is going to be relevant to this, there's actually two ways you can work this out, but the most obvious one is to use force is mass times acceleration. And then I can work out the acceleration from the change in velocity divided by time. So let's do it that way. We've got a change in velocity from 0 to 5, well that's 5, divided by a time, which is 0.6. If I do that calculation, 5 divided by 0.6 is 8.3 recurring, and that is meters per second squared. So that's my acceleration. I would then times it by the mass, which is 0.12. So times 0.12 is 1. So I've got an answer of 1 Newton. There you go. I could also have done this using my impulse equation if I'd wanted to, which is the change in momentum divided by time is force, and then bear in mind that momentum is mass times velocity. So it's actually the same calculation, but either way would work. Question 8. So a uniform rod XY of weight 2.0 newtons has a length of 80 centimeters. The rod is suspended by a thread 20 centimeters from the end X. So that is here. A weight of 5 newtons is suspended from end X. Okay. So you can see that on the diagram here. Okay. A student hangs 6 newtons on the rod so that it is in equilibrium. So remember, that means that it's staying balanced. It's not going to come up or down on either side. It's going to stay level. What is the distance of the 6 newtons from the end X? Okay, and this is another situation you're going to see where this could potentially be a trap, or potentially be somewhere where you could easily make a mistake. So, what's going to make this in equilibrium is if the downward moment on this side is the same as the downward moment on this side. So I need to know what the moment is over here to know what the moment has to be over here. So the moment on this side, remember, it's the force times the distance. So the force is 5, the distance is 20 centimeters. Normally I would convert this to meters, but the whole question is about centimeters, so it makes no difference. So I'm going to stick with centimeters for ease. 5 times 20, that is 100. So my moment is 100 newtons centimeters. So I know that my moment on this side also has to be 100. So what I now need to do is work out the moment here. The tricky thing is I've also got to take into account this rod, right? So this part here is a piece of rod that is 20 centimeters long, and it is pulling down in this direction. On this side, I've got another, well, its hole is 80. I've used 20, so there's 60 centimeters on this side, right? You can see that there's 60 centimeters of rod over here, which means there's significantly more over here. So ignoring all these other weights that are going on, this would naturally swing down on this side because there's more rod there. That means there's a moment there, so that moment has to be taken into account. Now I know there's 20 centimeters here, so that 20 centimeters up to there is the same, right? I've got 20 centimeters up to there as well. So that bit and that bit, this section here and this section here are going to cancel out. They're the same. Okay, so the only bit that matters is this section here. And that is 40 centimeters long, this section, because I've used 20 here, so 40 centimeters left, right? The center of that 40 centimeters is in the middle because we were told that it is a uniform rod. So that means that the weight is equally distributed along the whole rod. So the center of mass of that section is in the middle of it, which means that it is, if this is 40 centimeters long, it's at the 20 centimeter mark. So I have a distance of 20 here and a distance of 20 here. So that distance for that section from the string to the middle of that center of mass there is 40 centimeters. That's important. So 40 centimeters to here. Now it's of uniform length, uniform weight, which means that this bit here has the same mass as this bit here. Okay, because it is uniform, each bit has the same amount of mass in it. Okay, so this much here, this much here, this much here, this much here. Okay, you can see that this is 40 centimeters long and it's half of the whole thing. So it's half of this whole rod, okay? Because half of it is there, half of it is there. So the whole thing was 2 newtons, half of 2 newtons is 1 newton, right? So I've got 1 newton already pulling down here. So that means there's already a bit of a moment there. Let's work out what that moment is. So I use the same equation. It's going to be the force times the distance. So 1 times 40, that is 40. So I have a moment on this side of 40 newtons per centimetre, so 40 newton centimetres already. Okay, so I have 100 here, 40 here. That means I've got to add on an extra moment on this side to make up to the full 100, so they balance out. So, what's the difference? Well, it's 60, right? The difference between 100 and 40 is 60. So I need to have another moment of 60 newton centimetres on this side. I'm going to get that by placing that 6 newton block, or 6 newton weight on it. So let's work out where that needs to go. Is m equals fd. So if I rearrange that, the distance is going to be the moment divided by the force. So if I do that, I've got 60 divided by 6, which is 10 centimetres. So you're probably thinking, whew, that was a lot of work. I've done 1, 2, 3 different calculations, plus all this fiddly stuff in here, and I finally got my answer. It's 10 centimetres. Oh, look, there's my answer, 10 centimetres, boom, done. If you did that, that's where you're falling into the trap. Because we highlighted at the start, what is the distance of the 6 newton weight from the end x? That 10 centimetres we've just worked out is the distance from the pivot, right? So we're saying that we're putting it here, 10 centimetres from the pivot. But we need to know how far is it from the end x. Now x is 20 centimetres further away. So 10 plus 20 is 30. So the answer is actually D. Okay, and it is very, very easy to fall into that trap because you've just done all this work, you're feeling tired because you've just been focused on that and you want to get on to the next question because you're aware that you've spent a long time thinking about the same problem, which is fair because it is a tough problem. This is a really tricky problem. It's an A star kind of grade question, so it is there to distinguish the students who are doing well at physics and the students who are doing amazing at physics. Right? It's meant to be there to get those for those students that are getting A stars. Right? So if you slipped up there, don't feel bad. It is the kind of question that it's designed so that people slip up. So the message to get from this, the kind of lesson to learn from it is persevere, break down the problem into different sections, just like we did with this rod, and then make sure your answer matches exactly what they're asking for from the question. Because if you miss this bit, if you miss the fact that it says from end X, you're going to get the wrong answer. Question 9. A wooden plank rests on equilibrium on 2 rocks on opposite sides of a narrow stream. 3 forces P, Q, and R are acting on the plank. Here's P, here's Q, here's R. How are the sizes of the forces related? Now, what it's asking me is, how do these forces combine to make the the plank sit on these rocks like this? So if the rocks are holding this still, it's not moving, I know that the forces must be balanced, right? I know they must have a total of 0. Remember, it's like a force diagram, so I've got 2 going up and 1 going down. So I know that the 2 going up must combine to have the same total force as the force going down so that it all cancels out. I also know that P and R must be the same size, but that's not relevant to this question. So let's go through the options. I have P and Q equal R, so I'm saying that this force plus this force equals this force? No, because then this force would be huge and it would be making the whole thing tip up in that direction. So it's not that. P plus R equals Q. So this one plus this one equals this one. That's what we just said, right? That's 2 ups and 1 down, so they're cancelling out. So that looks correct. P equals Q equals R. So I know that P and R are the same size, so that makes sense. But then P and R and Q should not all be the same size, because then the total of these two together would be twice as big as that, and it would be taking off into the air. So that can't be right. Question D, so answer D, we're saying that this force is equal to this plus this. So again, that doesn't make sense, because these two would they would cancel out and then it would fly off. So no, it has to be the only one there. So it is B. There we go. Question 10. A ball of mass 0.16 kilograms is moving forward at a speed of 0.5 meters per second. A second ball of mass, I'm going to circle this, 0.1, and it has a speed of 0.5 meters per second when it's after it struck the ball. Now I've circled these to show that they're separate. We are asking what is the speed of the first ball after the collision. So with questions like this, sometimes it helps to draw them. I've got my first ball. This is ball 1, and it is moving, and ball 2 is stationary. So that is before. Then afterwards, I have my second ball, and it is moving, and the first ball is doing something. We want to know what. So this is after. What I can then do is add the numbers in. So I know that this is 0.16, which means it's still 0.16 afterwards. That mass doesn't disappear. This was 0.1 kilograms, and this is 0.1 kilograms as well. Now the first speed we said was 0.5 naught before the collision. After the collision, the second ball has a speed of 0.5 naught as well. So this question then is asking how much speed has this got. So this is a collision question, so you should be immediately thinking momentum. You should also be thinking momentum because you've got masses and speeds together. So my momentum equation is the mass times the velocity. And the key thing to remember for this question is momentum is conserved. So that means momentum before equals the momentum after. So if I total up all these momentums at the start, I will get the same total as all the momentums at the end. Let's give that a try. So let's work out the momentum of this ball before the collision. I'm going to do as mass 0.16 times by its velocity 0.5. So I'm going to go, I'm going to do it over here. So 0.5 times 0.16. If I do that, 0.5 times 0.16, I get an answer of 0.08 kilogram meters per second. Our second ball before the collision has no speed. So we know that if it has no speed, it's going to have no momentum, because 0 times whatever mass is still going to be 0. 0 times anything is 0. So that's the start. Afterwards, we know that this second ball is now moving, and it has a mass of 0.1, and it is going to be going 0.5 meters per second. So 0.1 times 0.5. I can do that in my head, but I'm just going to not take any risks. 0.5 is 0.05. So I know that this ball has momentum of 0.05 kilogram meters per second. And as I said, the momentum at the start is the same as the momentum at the end. So I know at the start I had 0.08, at the end I have 0.05, which means I've lost 0.03 somewhere along the way. So that 0.03 can only be one place, it has to be in this ball. So I know the momentum here is 0.03 kilogram meters per second. So I'm almost there. I know that this ball has a momentum of 0.03. What I now need to do is work out its speed. So speed is momentum divided by mass. So I can go 0.03 divided by its mass is 0.16. If I do that, I get 0.1875. Now that answer doesn't match any of these exactly. So I have two choices. Either I go, ooh, this must be wrong, or I look to see if it's similar to any of these. Now you'll notice that all of these are to a maximum of 2 significant figures. Okay, this number here, my answer, is 4 significant figures. There's lots of extra decimal places. So what I could do is I can put this into 2 decimal places to check before I start spending all this time trying to work out if I need to do it again. So let's do that. I've got 0.1875. So if I round that to 2 decimal places, that bit's there, the 7.5 is going to round up, right? So this is going to become 0.19 meters per second. Ah, look, that's great. That matches an answer now. So that must be my answer. If I did that and it didn't match one of these answers, I would check it straight away, right? I would absolutely go and have another work through that question. But generally speaking, if it's close, it's probably the right one. You just need to round it to the right number of figures. Question 11. A ball is at rest on the top of a hill and it rolls down the hill. At the bottom of the hill, the ball hits a wall and stops. Which energy changes occur? So I'm looking for the energy changes in being at the top of a hill to rolling down a hill to hitting a wall and then stopping. Okay, so I've got 3 different transitions there. Okay, from hill to rolling, from rolling to wall, and that's it. So if I'm on the top of a hill, the key thing is I am high up. So high up means it is to do with gravitational potential energy. So it must be one of these 2, okay, from that first piece of information. My second step is I am rolling down the hill. So rolling means moving. Moving means I must have kinetic energy. So the only one that has kinetic energy in second place is B. So B is looking pretty likely now. The third part is you hit a wall and stop. So we've got rid of that gravitational potential energy. We've got rid of our kinetic energy because we stopped, so that energy has to go somewhere. Remember, energy is usually wasted as heat energy, right, or thermal energy. We have another word for thermal energy, and that is internal energy. It's the energy stored inside particles when they are vibrating. So that is going to be our answer because it has to be, well, the only ones with internal energy in the right place are these 2. The only one that has all 3 in the right place is B, so it has to be B. We know that. The thing to really give that one away is the kinetic energy in the second place because you know that the rolling is the second step, but you should still go through all 3 just to be sure. Question 12. A student cycles along a level road at a speed of 5 meters per second. Okay, so it's flat and they're going 5 meters per second. The total mass of the student is 120 kilograms. I'm already thinking probably something to do with momentum because I know they've got mass and velocity. The student applies the brakes and stops. They stop over a distance of 10 meters. So what is the average braking force? So there's a few different ways to approach this question. The easiest way, you can do it with momentum, but there's actually an easier way to do this question, which is to look at energy. Because I know that I'm looking for a force, so I should be thinking, what force equations do I have? So I've got F equals ma, and then I'd have to work out what a is because I already got m. A would have to come from the change in speed divided by time, but I haven't got time, so that's going to be a problem. It's not going to work, so let's probably get rid of that one. Next one I know is I've got the force is the change in momentum divided by time. I can already see that's going to have the same problem because I need time, so that's probably no good. Any other force equations I know? Well, I know that work done is force times distance. That's good because it's got a force and I know the distance because that's here. So I need to know what work done is. Work done is an energy. So what kind of energy can I calculate from this question? Well, I've got a mass. So I've got a mass and a speed. So mass and speed can tell me kinetic energy. So kinetic energy is the mass times the velocity squared divided by 2. And remember, because of the conservation of energy, all the kinetic energy is turning into the work done. So it's all being transferred. So I know that these two numbers, the kinetic energy and the work done, are the same. So let's do that. So for kinetic energy, I am going to do the mass, 120, times 5 squared divided by 2. Now, because I don't want to mess this up, I want to make sure I do each of these bits carefully. So I could try and type it all into my calculator in one go, but it's probably safer to do 5 squared first, so that bit, and I get 25 meters per second squared. I then times it by the mass, and then divide by 2. And that gives me a kinetic energy of 1,500 joules. So that means my work done is 1,500. I can now go rearrange this. Force is work done divided by distance, which is 1,500 divided by a distance of 10 meters. So if I do that, 150. So let's check. There it is, 150. That is my answer. Question 13. A water manometer is connected to a gas supply. Now, I have never heard of a manometer before in my life. Doesn't matter, because they're showing me what it looks like, and I can see it's a tube with some water in it. Okay, so that's all I need to know. It doesn't matter what it is or what it's for, I just need to know the information in the picture, which is why they've done it, right? There's a gas leak and the pressure of the gas fails. So some of this gas is coming out in a kind of puffy jet here, right? So my gas is coming out here in a kind of puffy jet. So what I need to know is what is going to happen to the water level at P and what happens to the water level at Q. So if the gas is coming through here, it was originally putting a force on there. It's like blowing through a straw, right? And that's going to push the water down. And then that means Q is coming up this side. If we have less pressure, because some of it is escaping out here, that means there's less force on here, which means it's not going to push the water as far down. So P is going to have to come up. If P comes up, it's a fixed amount of water, so Q is going to have to come down. So that's what I'm looking for. P goes up, it's going to have to be C or D. Q goes down, so falls, falls. The only one that works for both is C. So C is my answer. Okay, now for question 14, there's a little bit of a bit of skill involved with using the equations. So let's have a look at what it is we need to do. We have a submarine, and it is 20 meters below the surface of the sea, and the pressure due to the water at this depth is P. Okay, so we're talking about pressure, so we're immediately thinking we're going to use one of the pressure equations. On another day, the submarine is 26 meters below, so it's gotten deeper, and this time it's in fresh water. Before, it was in the sea, so that's salt water. The density of the seawater is 1.3 times greater than the density of the fresh water. What is the pressure due to the fresh water at a depth of 26 meters? So, no actual calculations are really needed to be done with this, but it does require us to fiddle with the equations a little bit. So the equation we need is pressure is density times gravity times the height of the water above the object. Okay, we're going to use that equation. We're going to use it twice. We're going to use it once for in the salt water. So I'm going to put a little S there, and that's the density of the salt water and the height of the salt water. Gravity is going to be the same in every case. And we also have the pressure equals density times gravity times height in the fresh water. So let's put a little F there to say that that is that one. Okay, now we know that the height in the salt water, here it said it was 20. So we can rewrite that. It is pressure in the salt water is the density of the salt water times by gravity times by 20. Okay. For the fresh water, it was 26 meters under. So that is density of fresh water times gravity times 26. Okay, now this is where this bit comes in. We've said that the seawater is 1.3 times the density of the fresh water. So I'm going to put that over here. We've got the density of the seawater is 1.3 times the density of the fresh water. Okay, so what I'm going to do is I'm going to replace the density of the seawater with this. So I've got pressure in the seawater is the 1.3 times the density of the fresh water now times gravity times 20, and we've still got pressure in the fresh water is density of the fresh water times gravity times 26. Now for this equation, we've actually got two numbers in there now. Okay, so there's that number and there's that number. So what we can do is we can times them together, because this is all times, to combine them, to get it out of the way, because otherwise we've got numbers floating around in different places. So let's do that. So we've got pressure in the salt water is density of the fresh water now times gravity times 1.3 times 20. 1.3 times 20 is 26. And look, this and this are the same, right? You've got the density of the fresh water times gravity times 26. So it's the same thing, right? We're saying that the pressure in both those cases is equal to the same thing. So the pressure is the same, right? That's what we need to know. So if we're saying what is the pressure due to the fresh water at a depth of 26, it's not 1.7 times greater, it's not 1.3 times greater, and it's not divided by 1.3, it's the same, it's just P. So our answer is B, right? Now with that question, you have to be really careful, because there's a lot of you fiddling with these equations. It's a very difficult mathematical question that doesn't actually really use numbers. It's quite interesting. The actual science involved isn't too tricky. It's just being able to manipulate these equations to see what's actually happening. So that's the challenge there. Again, this is probably an A or an A-star question because of that. And you do have to be really careful, because if you put one of these numbers, like the 1.3 for example, if you put that over this side instead of this side, you're going to actually end up with answer D, which is wrong. And if you again put it in a different place, or you use these equations here wrong, you're going to get one of these other two answers as well. So it's very easy to make a mistake with this, which, you know, it's something you have to be really careful of. So for questions like this, you need to practice rearranging your equations and being able to put equations together. That's the really key bit, which we're going to make sure we practice a bit more next year, because that's something that's going to come up a lot with our electricity topic. Question 15. A cylinder with a tap contains a fixed mass of gas X. So the mass is constant. It's always the same amount. The gas is contained by a piston, which can move freely towards or away from the tap. So this bar, this flat section here, can move left and right as we want it to. We are going to open the tap. So we're letting the gas in this section here move. And it might be moving out, it might be moving in, we don't know. The idea is that this section is going to change pressure because we've opened the tap. And it's going to change until it's balanced with the air. So it's going to have the same pressure as the air pressure. What we need to do is work out what that means when this moves. So this bar has moved because the pressure on this side has changed. It's moved to the right, which means that the pressure on this side pushed it to the right. So we can assume that the force this side was greater than the force this side, therefore the pressure this side was greater than this side as well. This side is now at atmospheric pressure. It's the same pressure as the air, so that is our key fact. Let's look at our options and see what we have. So we're saying that before opening the tap, gas X had a pressure less than the atmosphere. No, otherwise it would have moved to the left. It didn't, it moved to the right. It was the same as the atmospheric pressure. No, because then it would have stayed still. So we know both of those are wrong. It was more than atmospheric pressure. So it's pushing that way. That's what we just said, so it should be that one. And it's also here, so it could be that one as well. So we've got two options so far that are looking good. After opening the tap, the bar has moved to the right, and it's going to keep moving until the two sides are in equilibrium and there's no resultant force pushing it in either direction. There's no resultant pressure, meaning that the pressures have to be the same size. So let's check. We've got more than atmospheric pressure. We know that's wrong. We just said they're the same size. More than, no. Less than, no. Same as atmospheric pressure, yes. So that answer there, D, is the one it has to be because it is the same there. Okay, it's worked. There's ticks both sides. Question 16. Liquid evaporates from a beaker. What happens to the temperature of the remaining liquid, and how does this temperature change affect the rate of evaporation? So, if something's evaporating, remember that is the hot particles leaving, which means that the cooler particles are left behind. So what is going to happen to the average temperature, or the average heat, sorry, it is going to drop, right? So I know that it has to be there or there. It has to be decrease or decrease. It's not increasing. Now, if I am decreasing the temperature, that means that it's going to have less energy, which means that it's going to be more difficult for it to evaporate, right? We know this because water evaporates very quickly at 100 degrees and it evaporates very slowly at 20 degrees. So we know that the rate of evaporation has to decrease, which means the only one where we match up is answer A, where it is decreasing on both, decrease and decrease on both sides. Brilliant. Question 17. Which quantity does not change when there is an increase in temperature? Density, diameter, length, or mass are our questions. So, for this one, we are looking at how each of these things is dependent on temperature. So, there's something we know changes because of temperature. It is pressure or volume, okay? Because we know this from our heat topic, that if the temperature of something changes, the particles are moving faster, which means they collide with each other more and they push each other apart. So hotter things get bigger, cooler things shrink. So if the volume is changing, how is that going to affect these four things? Now remember, density, we said, is the mass divided by the volume. So if the volume's changing, that means that the density must change as well. So density changes in this situation, and the question said, does not change. So that's not it. The diameter of a hole in a metal nut. So remember, diameter is the distance across a hole. So clearly not, because that's about size. The length of an iron rod, again, that's talking about size, so it's not that. The mass of a metal coin. Now, the mass is not affected by the volume. Density is, mass is not. So that is something that has not changed. It's the only one, so that must be our answer. Question 18. A thermocouple is used to measure temperature. Remember, a thermocouple is an electric thermometer, or a data thermometer, or a computer thermometer, however you want to call it. Which is an advantage of using a thermocouple instead of a liquid in glass thermometer? Liquid in glass just means the kind we tend to use in like old-fashioned schools. We actually have thermocouples in our school, which is great. The liquid in glass one is the more traditional one, where you might see mercury or some kind of red liquid inside it. Okay. So, which of these is true? It can measure temperature in a range from -10 to 110. It could do, but remember, thermocouples are probably going to measure in a whole range of different temperature ranges. Okay, it could be from extremely cold to extremely hot, or actually much smaller ranges as well, depending what it's designed to do. So that's not necessarily the answer. It's unlikely that that is the answer. So let's keep moving. I'm gonna put a little cross there. All right, B. It can measure temperature changes rapidly. Again, it is quite likely that it can measure temperature changes quite rapidly. Is it more quick than a liquid in glass thermometer? Again, it's pretty close to cool. I'm not certain that that is going to be the right answer. So let's put a question mark there, because it is probably quicker, because remember, data, electronics tend to work quicker, but it's not entirely clear. That could be the right answer, depending on the thermocouple. C, it has a linear scale. Well, they both have linear scales, right? They both go up the same amount every time, so that's definitely not it. And D, it's more sensitive. Now remember, sensitivity is determined by the materials they're made from, right? So a thermocouple is typically made of metal, and it will depend on how much metal is used, how big or how small it expands to when it works. So it actually is very variable again. It's just like our answer for A, where we're not really sure. It depends on the thermometer. So again here, it depends, because you might have an extremely sensitive liquid and glass thermometer. They can be extremely sensitive, so probably not the right answer. So you can see here I've got 3 that I know are probably wrong, and 1 which I'm questioning, so that is the one I should go with, clearly. And that is the right answer. B is the correct answer. Question 19. A block of copper has a mass of 2 kilograms. It absorbs 12,000 joules of thermal energy. So I'm starting to see key bits of information. The specific heat capacity is 385 joules per kilogram Celsius. What is the temperature rise of the copper when this block is absorbing that heat? So I know the equation I'm using is my specific heat capacity equation, which is energy is mass times specific heat capacity times the change in temperature. So I need to rearrange it so that I've got my change in temperature here on the one on its own. So let's rearrange that. I'm going to get my change in temperature is the energy divided by the mass times the heat capacity on the bottom. So if I use that now, I am going to put these numbers in, and it becomes very easy at this point. So 12,000 divided by 2 times 385 on the bottom. Before I do that, I'm just going to check my units. So this is joules, that's okay. This is kilograms, that's okay. The answers are all in Celsius, this is in Celsius, so those are fine. You want to be really careful when you're doing calculations like this, especially when there's lots of numbers, that all the numbers are in the correct units, or at least in the same units. So it works fine here. I'm happy to continue with what I'm doing. So I'm going to do that now. So 12,000, sorry I missed a 0, 12,000 divided by 2 divided by 385. And I do that, and I get 15.5844155, a whole list of numbers. So obviously it's not going to match any one of these exactly. These are all to 1 decimal place, so I need to round this to 1 decimal place. That second decimal place is an 8, so it's going to round up. So my answer is 15.6 Celsius is the temperature change. The answer is asking for a rise, which is a change. So I don't need to worry about adding this to anything or anything like that. That is my answer, and it matches here. So that is perfect again. Great. Question 20. A teacher demonstrates an experiment to a class. A boiling tube is filled with with water and some ice. I don't know why I said diameter, sorry. So some ice is trapped at the bottom of the tube. The teacher then heats the boiling tube in position shown until the water at the top boils. So here, that water is going to boil. And it's telling me the ice does not melt. Okay. So the water at the top is boiling and the water at the bottom is not melting, which means it's at freezing, right? It is 0 degrees here and it is 100 degrees here. So what does this demonstrate? So must be one of these. So I'm looking for the one that I know is the most true. Right. So first one, water is a good conductor. If water was a good conductor, this would be conducting the heat down and this would melt. So that is not correct. Water is a good convector. Again, if it was a good convector, it would be water that would be moving and this would melt. So I can't show either of those things with this experiment. I know it has to be a poor conductor because I'm not seeing this warm up. So the question is it a poor conductor or a poor convector? So the logic I should be using is this mesh here is going to be preventing a significant amount of convection, right? So from this experiment, I can't tell whether or not it's a poor convector. Just as I couldn't tell if it was a good convector. Right? I don't know if either of these things are true because this setup is not allowing me to check that. What it does tell me is it is a poor conductor because the water is still in contact with itself, so it should be able to conduct the heat through if it was a good conductor. It's definitely not. It's a poor conductor. So that is our answer C. So that's what we put. Question 21. A metal cup has a plastic lining. The cup is filled with hot water and held by hand. Which statement about the transfer of thermal energy from the water to the hand is correct? In the plastic, no energy is transferred directly between adjacent molecules. Can plastics conduct heat? Yes, they're not good conductors, but they can do it, so that is not correct. B. In the plastic, fast-moving molecules interact with free electrons, making free electrons move very quickly. It's plastic, free electrons only exist in metal or graphite, so that is not correct. Question C. In the metal, energy is transferred only by electrons. No, again, because we know that the particles in a metal can vibrate, so there is another way it can transfer heat. It does transfer by electrons, but it's not only by electrons. That's the problem. Last one. In the metal, energy is transferred by electrons, yes, and by vibrations in the lattice, yes. So it's that one. That is my answer, D. Question 22. So in this example, a man can either take an escalator or a lift to travel up 2 floors. And you can see both of those here. The escalator takes 20 seconds to carry the man between 2 floors. The useful work done against gravity is W. The useful power developed is P. The lift takes 30 seconds, so it's 10 seconds more to carry the man between the same 2 floors. How much useful work against gravity is done by the lift, and how much useful power is developed by the lift? So they're going the same height, right? So if they're going the same height, they're gaining the same gravitational potential energy, which means that the energy must be the same in both situations. So that is our first thing to look at. In our table, we're saying that work done, remember, is energy. So we're saying that in our example, the lift is doing more work than on the escalator, which is definitely not right. We just said they're the same. So B is also wrong because we said they're the same. So it has to be C or D. Next then, if we know that the energy is the same, what's going to affect the power is how long it took. Now remember, power is energy divided by time. We don't know the specific energy, but we know the different times. So remember, if we divide something by a larger number, we get a smaller answer. If I was to divide by 10, I'd get a tenth. If I was to divide by a millionth, I'd get a million, I'd get a millionth. So you can see that the bigger the number I divide by, the smaller the answer I get. So if I'm dividing by 20 in my in my escalator, I'm going to get a larger answer than if I divide by 30. So that means that in the lift, the power is smaller. So that is this one or this one. Again, this is the only two that match up, so C must be my answer. Question 23. I think this is, right. A 40-watt lamp wastes 34 joules of energy every second by heating its surroundings. So 2 numbers there. 40-watt lamp, 24 joules every second. So that means that the power of this lamp I can work out as well, right? Because it is, power is energy divided by time. The energy was 34, the time is 1. I definitely don't need a calculator for that. My power is 34 watts. So if I've got 40 watts going in, 34 coming out as waste, I need to work out what is the efficiency. My equation for efficiency is the total useful out divided by total going in. So, looking at that then, this number here, 34, is not my useful energy because it is waste. Okay? Question told us it's waste. So that means what's left over must be the useful bit. So what's left over? I used 34 out of my 40, meaning there is 6 left over. So my efficiency is going to be 6 divided by the total input was 40. 6 divided by 40, let's do that. 6 divided by 40 is 0.15. Now, all my answers are percentages, okay? So I'm immediately seeing a 0.15 here, but I haven't converted my answer into a percentage yet. Because remember, a percentage, you have to times by 100. So do that, and I get 15, okay? And that is also one of my answers. So that is the correct answer. And again, you can see that this is where there's a trap coming in. You can actually see that this one is a trap as well, because this would have been what you would have got if you'd used the 34 instead of working out that actually it's 6. So there are plenty of places in this, like with the other ones, where you might slip up. So be very, very careful. When doing these questions, think about what is the logical answer, right? So if I've got 6 out of 40, don't just trust that it's 0.15. Think about it. I know that 6 is more than 4, and I know that 4 is 10% of 40. So I should be thinking, well, I know it's more than 10%, so I can go from there. Next question. A column of liquid has a height h, a mass m, and a density ρ. The gravitational field strength is G. What expression gives the pressure due to the column of the liquid? So, the pressure, we said previously, is P equals rho g h. Fell into my mistake there. We actually did this earlier when we were talking about the liquid moving inside the tube, which was here, right? That really long, difficult question. So we've used that equation before. So all we need to do here is say which one is the right one. It is this one, D. So be really careful, don't make the same mistake I just did. I wasn't thinking about it carefully, and I just wrote down the first thing that popped into my head. So make sure you're checking that. It is density times gravity times height. So that is my answer for that question. Almost done. Next question then. The diagram shows 2 mercury barometers. Remember, a barometer is just a piece of equipment that measures pressure. So the right-hand diagram, this one, shows the tube of a... Oh, sorry, it's cut off a bit of the information. A tube of a larger diameter. Okay, so the diameter of this one is larger than this one. There is a vacuum above the mercury in both tubes. So this section here and this section above it, either here or here or here, depending which one we choose, or all the way down, is empty. We know that that is the case, right? Which label position on the right-hand tube shows the mercury level in the right-hand tube? So we're saying, is the mercury going to sit above the other tube? Is it going to sit at the same level as the other tube, below the other tube, or right at the bottom level with the liquid at the bottom? So, the key thing to think about this is it's all to do with measuring pressure. So, don't fall into the misconception that it is the vacuum that is holding it in place. It's not. The vacuum has nothing to do with this. It's just there. Okay. What is keeping this mercury pushed up is the pressure on the liquid around it. The pressure of the air coming down on that liquid is pushing down on here, which means that that pressure here is pushing upwards and keeping that liquid inside the tube, right? So, the pressure on here is the same as the pressure on here, right? It will always be the same because the pressure is due to air, and the air is the same because we're doing this experiment in the same place, we're assuming, right? It's not like one of them's done at the top of Everest and the other one's done at the bottom of the ocean. So, we know that the pressures are the same, so if the pressures are the same, it should be pushing them to the same height because it's got the same amount of force behind it, right? If it's pushing it to the same amount of height, our answer is B. That is our answer. Next question. At minus 39 degrees C, the liquid mercury solidifies. So minus 39 liquid mercury solidifies. So it goes from a liquid to a solid without changing temperature, okay? So that's really, really key. Okay, the temperature is staying the same. Which row shows whether the mercury absorbs or releases energy and what happens to the bonds between the mercury in the atoms? So we're going from a liquid to a solid here. Okay, so let's talk about the bonds first, because that's the easiest one. If I'm turning from a liquid to solid, I am making bonds. I am fusing those atoms together, which means that the bonds must be getting stronger. Right? So I know the answer already is A or C. Right? It's not going to be B or D, which is lucky because D is being cropped off by the printer. For energy, this is going to be to do with my latent heat. So the energy, if I'm melting, means I'm heating it up, which means that it is absorbing energy because I'm giving it some energy to make it melt. That means that freezing or solidifying must be the opposite, which means it is releasing energy. So my answer must be C or D for that, not A or B. So it must be C, because it's the only choice which matches for both. Sorry, I messed that up a little bit there. Next question, 27. A model thermometer consists of a flask of coloured water, which is here, with a stopper in the top and a glass passing through it, which is this tube here. So it's a glass tube going through that. The thermometer model can be changed in one of two ways. We can either make the flask bigger, so this becomes bigger like this, or we can make the tube have a larger diameter, so it's going to be a wider tube. Which statement is correct? So, are we saying that only using a larger flask would increase the sensitivity? Remember, sensitivity is about how detailed a measurement we can make. Are we saying that only a wider tube would do that? Or are we saying that both of those things could, in fact, increase the sensitivity? So if we think about this, this thermometer is based on how the size of this water changes as it changes temperature, right? So if I heat this water up, for example, that water is going to vibrate more and it's going to make itself expand by pushing on itself, right? So that means if I have more water, the amount it expands is going to be more, which means it's easier to measure. Now, if it's easier to measure, that means I can measure small amounts of it, right? So I know already that having a larger amount of water means I can make smaller measurements, meaning it is more sensitive. So I know that having a larger volume of water can increase the sensitivity. So I know already then that B must be wrong, because I know that the flask is going to affect this. Next one then, does the width of the tube affect this? Now the width of the tube is not really containing any water, right? It's a very small amount of water, so increasing that width is not going to increase that sensitivity, right? In fact, having a larger width means that you're letting more water get up there, or more liquid get up there, without it actually having to rise very much, because it's a wider volume, right? So you've got more in a smaller height that's going up. So that means actually making the diameter of this tube larger will decrease the sensitivity. So we definitely know that this is wrong, and we also know now that the option for both of them is wrong. It has to be the one that only talks about the flask. So it is A. That is our answer. So I'm going to circle A. Final multiple choice question, I believe. Yep. So 4 objects are made of the same material and have the same mass, and they are at the same temperature. So all three of those things have been controlled. We know they are all the same. Each of the objects has a different surface area and a different mass. Which object emits radiation at the greatest rate? So I'm asking, how will the surface area affect the rate of radiation, and how will the colour or texture of it increase the radiation as well? So let's do the surface area first. If I have a larger surface, there is more space to radiate off energy. So I know that larger must mean more radiation, right? Think about on a hot day. When you're hot, you tend to spread out your body as much as possible to try and let yourself radiate off that heat. When you are cold, you curl yourself up to try and retain that heat, because if you're smaller, you've got a smaller surface area, you radiate less. So the answer here is large surface area is going to radiate the quickest. Now the surface, remember, we said that black materials are the best absorbers and emitters. So I know that something that is black and matte and dark and of a dull colour is going to be my best emitter. Things that are shiny like mirrors and metals are very bad emitters. So that is my answer here, okay? So now I know that it has to be A because it's the only one that has both. So there you go. That is the multiple choice part of this paper. As you probably saw, some of the questions are probably more difficult than you get in the extended answer because they are actively testing that you don't make mistakes. In the extended answer, they try and make it fairly simple, not simple for you, but they are trying to give you room to show that you know how to use this information. Whereas here, they're really trying to make sure that you can spot mistakes and that you can work in a more logical and thorough way, right? So they're not trying to trick you, but there's a lot of places that you could fall into traps or you could get yourself mixed up. So you have to be really, really careful with that for the multiple choice paper.